Okay. I am going to talk about something which I assume for you is might be new. There's been a flourishing of papers recently about a possible new phenomenon, which I'm going to explain. It goes under the name Planck stars, black hole to white hole tunneling, and things like that. So what is it? Is the idea that there could be something shortening the lifetime of a black hole with respect to the Hawking time. It's a possibility that a black hole could decay very much like nuclear decay, so via a non-perturbative tunneling. And I'm going to describe why this is in fact, very plausible phenomenon abstractly. And the real question is how long it takes, and what can we say about it, the time it takes, and whether there can be any possibility of observing something like that. And the short answer, so to the summary of the talk up front, is that, of course, a black hole can decay because quantum mechanics allows it, and I will give you the detail of that. And we don't know how long it takes, but there are some indications and some preliminary calculations that it might take short meaning shorter than the Hawking radiation. There is a way of computing that, and I will sketch the way of computing the black hole lifetime under this decay. If it effectively comes out so short, I will say what this m squared means in a moment, then yes, we can observe black hole explosion from primordial black holes. And there have been papers suggesting that, in fact, we might already have observed them because some some fast radio bursts, some strong signals observed by radio telescope recently might have this explanation. This is, of course, very speculative. These signals might have all sorts of other origins. The good news is that if these signals have this origin, there is a very peculiar property they would have, a relation between distance and frequency that would allow us to confirm that they are this thing and not something else. So that's the story. In brief, we know, in fact, I think one of the surprises of the last 20 years of physics is that collapsed object in the universe, plenty. The universe is plenty of black holes, small, large. Recently with LIGO we observed a sort of larger than the stellar one, but larger than we expected. Of course, there are the galactic one as well. So the universe is full of collapsed objects. I put black holes into into quotes because, of course, one may be picky about what do I really mean by black hole. I just want to say something that collapses inside some form of horizon, a trapped horizon or a dynamical horizon or something. Now, what happens when a star collapses or when some matter collapses? Well, we have theories telling us, general relativity tell us that that's forever, that's stable, of course, because there's an event horizon that forms, so the lifetime is infinite. Quantum field theory in a classical geometry, of course, we know, thanks to Hawking and Gary and others, that there is a phenomenon that makes them evaporate and then presumably explode. The title of Hawking article was Black Hole Explosion, in a time which is m cubed in Planck unit, that's the standard Hawking evaporation time, which I'm sure you know, but just is important to remind you, is very long. So a stellar black hole takes 10 to the 50 times the life of the universe, 10 to the 50 Hubble time to evaporate. So it's immensely interesting in theoretical, on theoretical ground, is of no relevance, no astrophysical relevance whatsoever, right? Unless they're very small black holes or less. But that's what I want to discuss about. This is an approximation. We know classical GR is an approximation. It's a fact. It cannot be true because it's quantum mechanics. But this is also an approximation because it's quantum field theory on a dynamical geometry. It's also an approximation if you include the gravitons, right? Because it's a perturbation around the metric. So what you don't see is the non-perturbative quantum gravitational phenomenon. So typically you don't see tunneling. If you take a nucleus, if you take an electron inside a nucleus, or an alpha particle inside a nucleus, and you want to see with perturbation theory how long it takes to tunnel out, you get infinity. Right? You don't see it. So by expanding around the classical geometry, you don't see tunneling, quantum gravitational tunneling, a tunneling effect of the quantum gravitational field itself, which may connect geometries which are far away with respect to another, with respect to the Einstein equation evolution. So what I want to argue is that full quantum gravity does allow a different way of decaying for black holes, which is not the Hawking radiation, and that it might be that this is shorter. Now, m square in Planck units, here is an example, which is going to be relevant the phenomenological, the last slides, which is more phenomenological. If you take a mass of a small planet, or the mass of the moon, or something like that, 10 to the 24 grams. This is in grams, sorry. M cube. There's a mistake here. This is m cube is zillions of Hubble times, while m square is 1 Hubble time. Okay. So this means that the Schwarzschild radius of the moon is the order of centimeters. If you have a black hole of a millimeter or centimeters in the early universe, by Hawking radiation, it takes stable on our scales. If there is a phenomenon like that, it might decay now. So again, this is the same story. That's the prediction of classical GR. That's the Penrose-Carter diagram for a black hole that forms some matter that falls in. This is Hawking radiation, the Penrose diagram that is usually drawn, which I don't know exactly what it means. I think it doesn't mean anything. It means that we don't know what's happening there. This doesn't really make sense. But that's the usual story, right? Somehow, if there's evaporation, then it's not there anywhere, and this is something mysterious happening. Now, what I'm suggesting is that it might be that there is a decay and a quantum effect that allows sort of tunneling out of the black hole. Let me explain. You have some matter that collapses. This is a horizon that forms. Okay. Inside, well, whatever, outside there is Schwarzschild. We know that here curvature is very high, so we enter the quantum region, meaning we know that we don't know what's going to happen, what happens there. Now, the question is what happened there, and quantum field theory of curved space-time does not tell us what happened there, right? So it's definitely in a deep quantum gravitational regime. That's what quantum gravity is supposed to tell us. Now, one may say, and it's often said, let me, for simplicity, get rid of the matter and use null matter. So suppose you have a null shell because it's easier to do calculation, not for else. So you have a null shell coming in from infinity. So that's particularly easy because inside a null shell you have Minkowski. Okay, so if you have Minkowski here, Schwarzschild here, null shell comes in, it has a mass, an energy. It has a center of mass, so it's well-defined energy with respect to its center of mass, and it produces, and then you know the metric outside is an horizon. Now, one usually say that here its quantum region is high curvature, but outside the horizon, no. Outside the horizon, the curvature is finite. Therefore, there's no quantum gravity. Therefore, we can use classical GR, and classical GR tell us that the horizon continues all the way to infinity. Therefore, we know what happened outside. Okay? Now, strictly speaking, what I said is wrong. And why is wrong? Because the fact that it's not true that there are no quantum gravity effects here. There are quantum gravity effects which are small. Small effect can pile up and produce some effect. In fact, that's exactly what Hawking wrote in his original paper. That's the original Nature paper on black hole explosion. He says, we usually think that outside the horizon there's nothing quantum, but even though quantum effects may be small locally, they may still add up to produce a significant effect over the lifetime of the universe. Now, in fact, Hawking was wrong in a sense, because you don't really need that to have the Hawking radiation. But I think the point is right, because a quantum gravitational effect might pile up and give tunneling outside the horizon. How long would it take? We expect quantum gravity effect where something become Planckian. So if I use Planck unit, something becomes of order 1. The simplest possibility is that the curvature, R is a curvature, becomes Planckian. And this, of course, happens near singularities, right? Because it goes to infinity. So that's where we all expect strong quantum gravity effect. But there's something else that may come Planckian, which is a curvature multiplied by a time. Now, just stay at finite region outside the horizon of a black hole of mass m, and the curvature is m over r cubed, right? And if you are near the horizon, r is the order of m squared, so you get t over m squared of order 1, which is t over order of m squared. So just on, this can be done a little bit better. I've done here the most brutal way of doing it. So just on dimensional argument, it makes sense to expect that there may be some quantum gravity phenomenon also outside the horizon, provided that there is enough time to wait. And the typical long enough time phenomenon in quantum mechanics is tunneling, of course. So it's not true that we know for sure that the horizon is going to continue for infinity. Namely, it's an event horizon. It might very well that something happened here, so maybe this can be a dynamical horizon, a trapping horizon, something which looks like an horizon short scale, but it's not an event horizon. And I want to claim that we have good reasons to believe that something like that may happen. So there is some region in which the Einstein equation are violated, and this is a possible story of the world. So outside this quantum region, it's classical GR. There's an incoming shell, just shell because that's the only case in which I can do calculation, which bounces out or goes to 0 and continues. It generates a trapping horizon, and then there's some quantum region, and then it comes out, and the trapping horizon diminishes. So you have a trapped region and anti-trapped region here. Of course, you have Minkowski here. Inside the shell is always Minkowski, and outside is Schwarzschild. Now, this is an idea that has been put forward. If you look in the literature for this idea, it's very old. Everybody has talked about this idea. This is Frollo-Wilkowicki from in the late 70s. This is Toft with collaborators in 93. This is Asheker-Borgeveld in 2005. This is Modeste in 06. This is Hayward 06. This is all version of this story. What's new? What's new is the following, that the first technical, so far it was blah, blah, blah. All right, now I'm giving you a first technical result. Technical result is the following. There exists a metric which I've written here, I'll explain you what it is, which is an exact solution of Einstein equations everywhere in the 1 and 2 region. So everywhere except in this region 3, which is small. Small meaning compact. It lasts for a short time. I will tell you how much, and it goes just outside the horizon. Okay? So this is highly non-trivial. It's a tiny non-trivial result. In fact, if you're a relativist by formation, you look at this and you say, no, Carlo, this is impossible. Why is it impossible? Because I'm claiming that there is an exact solution of Einstein equation which has a black hole. This is the horizon of black hole. So this is Schwarzschild, the standard, okay? And a white hole. This is an horizon. This is an anti-trapped region. So this is if you look, the upper part is a white hole. If you look at the lower part, it's a black hole. So I'm claiming that you can put a black hole and a white hole in the same space-time with a black hole first and a white hole after. Now, everybody who has learned general relativity knows that this is impossible. So this is again is a incoming shell. Inside is Minkowski. Horizon that forms Schwarzschild, horizon white hole outgoing shell. So I'm claiming that this is true. Now, why it seems impossible? Because this is a black hole, but this is in the past, and everybody knows that if you extend the outside of a black hole, if you want to extend in, you can, and it's Kruskal, right? But Kruskal has the black hole in the future and the white hole in the past. So it seems natural that you can have something that explodes and then a black hole. But how can you have a black hole that goes out in the... Well, it is possible. Of course, it is possible by violating Einstein equation in this region, right? I'm saying that the gray region violates Einstein equations. That's quantum mechanical tunneling. And how is it possible? By starting from Kruskal... I'm going to build this for you, not with equations, but with a picture, which to me makes things easier. I start from here, and I cut the gray part. I cut the gray part. So in other words, I take a double covering of this. I open this up. This dark gray is isometric to this dark gray. This clear gray is isometric to this clear gray, light gray. I open it. I switch. I put something in the middle, and obviously I construct this solution here. So in other words, you can take a double covering of Kruskal, or in other words, you can cut two pieces of Kruskal, this one and this one, separated, glue them in some part, and this gives the external of my black hole. Yeah, the matching condition works. That's the point. Here? The matching is here along this line. Yeah, no, everything matches. Extrinsic curvature, C infinity. Yeah. If you think it's very easy, that surface is a T-equal constant surface in Schwarzschild, and so the geometry, the intrinsic geometry is what it is. The extrinsic geometry is the same because it's time reversal invariant. So in other words, what you can do is take the lower part, flip it, T minus T, glue, and since this is a, so it does work. We checked all the it's infinity the matching, so so everything works. We call the finger crossed because you're uncrossing this one. So let's look how this looks from in Schwarzschild coordinates. Because in Schwarzschild coordinates, if you have an incoming light ray, right, in Schwarzschild coordinates it never goes in. Schwarzschild only covers the outside. So it, is a frozen star. It's the old Russian picture of the black hole, right? So the matter that never goes in. If you look at a black hole, what you see is that things slowing down. Slowing down. So this is what Schwarzschild coordinate give you, because this 2m line is just the point of this. So in Schwarzschild coordinate, you see the light ray slowing down, staying there for a while. Then you have a little teeny bit where the Einstein equation are violated. The light cone here is the Schwarzschild light cone does that. So what happens in this light bit is that the incoming shell jumps from the ingoing to the outgoing light cone, which in these coordinates are very close, and moves up. And the external metric, which I've cut, it's uniquely defined by two parameters. One is the mass of the black hole, and the other is where I cut and glue, which can be coded equivalently either in sort of the distance of this point from the horizon, which you call little delta, or equivalent in what we call the bounce time. The bounce time, you put yourself at some finite distance, you compute the proper time from when you see the shell coming in and when you see shell going out. You take away 2r, which is sort of the time it takes the shell to go inside. And what remains is t. In the limit in which you take r away, this t becomes just finite, and it's the bounce time. And the relation between delta and t is just one is t is minus log of delta over m. Yes.
That's a free parameter.
Sorry.
That's a free parameter.
That's a free parameter of the geometry I'm giving.
Arbitrarily adjust it and make this region
Yes.
arbitrarily small.
Yes, that's right. As far as the classical theory is considered, that external metric is it's just a solution of Einstein equation for every n and every t. What determines it? Well, quantum theory. Right? We're not giving the dynamics. Let me go back. The Einstein equation determines the outside, but of course there is something undetermined because I can only evolve in the past domain of dependence. So I would not be able to evolve outside this line. I need something else to come in, and something else is delta, or t. So t is a bouncing time. It's time from here to here, which, as far as the classical theory, any t is good. Quantum theory is, if you want, imagine you have an atom that forms. Something collapses into an atom, and then there is you wait for uranium 2,000 years, and then it decays. So the outside geometry of something coming in, something coming out, is a parameter that you don't know, which is how long is the lifetime of the uranium. This is, you can compute it with quantum mechanics, and that's what I want to do. I want to do a quantum mechanical calculation inside to determine this t. Okay, so this is a. It's very similar.
Because the metric inside is cosmological, so it's a big time going into a big bang.
In fact, that's how we got to it. By there is all this work in loop quantum gravity on the loop quantum gravity bounds. Right. Our initial idea was that if you have some matter that collapses, goes in, then what happens? It gets a Planck density. A Planck density means some quantum pressure. And,
but we know that you have to violate some energy theorems, you have to have some negative pressure.
Inside this region, you violate everything.
Yeah, okay.
Everything you can think of is violated.
Yeah. So then it's easy, in cosmology I can write the bouncing solution for you.
Yes. Yes.
It's the solution of which theory?
Yes, sure, exactly. So you need a theory telling you what happened there. But in the case of the black hole, I think this is already a result because it says something which I think was not known before. Namely, a black hole can tunnel into a white hole by violating the Einstein equation only in a finite region. Okay? I mean, if you look at the literature, if you look at Gary papers, of course you can tunnel from you can do quantum tunneling in the universe of various kinds, but you always think of the universe as a whole. What I'm saying is that exactly. Now, let me choose a t and a delta, and then there's something very interesting happen. I choose an m, say lunar masses. I'll see. You'll see why I like lunar masses. And I compute the proper time outside and inside in my metric, and with m of the mass of the lunar, the time from here to here is sort of milliseconds. The time from here to here, I have a preferred frame, right? This is Minkowski. I have a preferred frame because I'm inside of something. It's the center of mass of everything. So I know what I mean simultaneity here in Minkowski. So I compute this time and this time. I have a metric, I have everything. This is a millisecond. This is a billion years. So the physical story is compelling. This is generativity, so this is time dilation. Time goes slower at the sea and faster at the mountain. The more you go inside the potential well, the more time slows. So what I'm saying here is if a mass collapses, time slows inside enormously, so the shell just bounces at the speed of light, sort of. The millisecond is a transit time for light, the black hole radius. So inside is a fast process, but because of generativity, seen from the outside, is an enormously slow motion. You see it in slow motion. And under the hypothesis of theorem squared, to which I'm getting in a moment, you can have milliseconds inside and billions of years outside. Okay, So what determines T? Quantum gravity, and which kind of quantum gravity do you have to use for this? A quantum gravity which is not formulated in terms of excitations over a given geometry. Right? That's the point of the story. Because the geometry itself is going through a tunneling here, through a quantum transition. So it's like, if you want to do double slit, you cannot take a trajectory and do quantum mechanics by perturbation over this trajectory, because there are two completely different trajectories that interfere. So this is loop quantum gravity. I'm not going into it. Loop quantum gravity is sort of tailor-made for these calculations, because the way is defined. These are the defining equation of loop quantum gravity. That you can write boundary states on a 3 geometry and transition amplitudes, which is a number associated to this boundary state. I'm not going to that. So loop quantum gravity, you have a space-time region, you put a geometry on the boundary, a state on the boundary, and you compute an amplitude, and that's it. So let me use it in this case. Whoops. The green is my initial geometry. The yellow is my final geometry. In fact, I'm just computing from this little bit to this little bit. And I compute the transition amplitude from going from the initial geometry to the final geometry. So I know the geometry outside because it's classical. So I know the geometry here. I mean intrinsic and extrinsic geometry, both. And I have a machine to compute. That's loop quantum gravity, to compute the transition amplitude. The way it works, of course, is via approximations. It's order by order calculation. So one way of looking at it is that you discretize this geometry here and here, and then you have a certain calculation to be done. So we choose a surface, an initial surface, and there's a convenient choice. We use Lemaitre coordinates. Lemaitre coordinates are very convenient for that. This is a t equal constant in Lemaitre coordinates. So we choose this surface here, which is this one, and it's time reversal, which sort of come here, which is this one. We know the geometry because we can write explicitly Kruskal in Lemaitre coordinates. So we know intrinsic, extrinsic geometry here. We discretize it. That's the structure of the spin network, the structure of a discretization. It's a spin form, so we discretize the ensemble. It's essentially it's a two 4 simplexes inside. You have one 4 simplex, which is bound by 4 tetrahedra, and another one. They glue by 1 tetrahedra, so you have a 4 tetrahedra down, which is a ball, and 4 tetrahedra up, which is another ball, glued by their external, which is a S2, a sphere, which is the sphere, which is this point here. So it's a ball here, this one here, a ball here, this one here, glued by the sphere inside, and you have 2 tetrahedra. So you do a calculation, blah, 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 and you come up with this expression. This expression gives the amplitude, and it's just a function of the parameters that determine the geometry. Okay? Assumed, which we are far from being able to prove, that the approximation discretization doesn't add additional structure. So you have an amplitude that depends just on the mass and the time. The only two parameters is external geometry. The modulus square of this is the thing that gives a probability. So you want, this is standard definition of transition time. You want the probability to be 1 minus 1 over E, which is the way you can define the transition time, assuming there is an exponential decay. Now, I wish I could tell you we have computed this is complicated expression here, the integrals, everything is perfectly well defined here and finite, but we cannot compute it. So we're struggling to compute this. We believe that if we try to extract the dependence of sort of the scaling with m of all this mess here, we get m squared. We have argument for that. I'm not going into this argument because it's sort of reading out these integrals and this sum. So assuming this is true, I'm saying there's a well-defined finite expression. If we had an infinitely powerful computer, we just put it in and spit out this number.
Carlo, if this were true, one expect the Stanley amplitude to be exponentially small, e to minus some axis.
Yes, it's that's the main warning. In fact, That would make the time very, 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 because that would be e to the minus 1 over h bar, which means h bar g, which means m square up, which is e to the minus m squared. So that would be infinitely, infinitely long. We have a number of reasons to believe that this does not work, does not happen here. One being that if you think in terms of function of path integral, that's the action term, but then there's a measure term. And the measure count how many states there are. And this is also exponential, but with the other sign.
Oh, so you think there is a calculation?
So it's plausible that there is a calculation. So we have this dimensional argument for saying, let me be clear. We have no solid proof that is m squared, right? But it's written here. We just have to do these integrals of this sum. So we will in
T square would mean that the time goes,
M square.
would mean that the time goes like 1 over
square root of h bar. That's right. That's right. That's
the calculation I expect.
That's what he's saying, yeah.
You say, okay, there's a measure term which could cancel that and leave it with a finite rational dependence, right?
The measure term is the entropy of the black hole.
No, I understand. However, you're not really actually at the black hole. There's some distance between the black hole. It's the size of this sliver. And I would expect a very delicate balancing between the positive exponential and the negative exponential. And the size of the sliver will turn up in that exponential. So if you change that parameter, even a tiny bit, you will still get an exponential suppression in the amplitude.
It's a different philosophy. What Rovelli is saying, and what you are saying is that this will be a completely standard essay.
Yeah.
I would say black hole can decay into 2 particles, and that's exponentially suppressed by a Boltzmann factor or instanton or whatever. I think what he says is that he found a new semi-classical trajectory. You're not talking about there is a trajectory because he can violate the energy condition. That's your point.
Well, yeah, it's violating Einstein equation, of course. So you can.
Trajectory, fully legitimate trajectory.
It's in another theory, but if I was trying to estimate the effect.
Oh, you are right. Yeah, if you in a standard estimate, of course, everybody would immediately tell you that it should be exponentially suppressed. But I think his point is that there is a because
Yes,
there is a trajectory which is not suppressed. That's what you're saying. Right?
Yes, yes. Well, yes, that's right. Let me try to address what you say. This delta, it's a Planckian. So in the calculation, we think we believe that we see the m square dependence coming out here, because if you take the approximation in which you put sharp the area of the surface surrounding this point, then you see immediately that t is infinity. This is stable. If you consider the superposition of, this is all discrete because it's loop quantum gravity, of 2 intermediate states, one with area A and one area plus a Planck area, then you see the interference between the two, and this gives immediately the m square. Then if you look at the next terms, this seems to be much smaller. So it's what you were saying, except that it's not finite, the distance between the horizon and the extra term.
So to make the exponentials cancel each other, you choose the size of this wedge to the Planck scale.
If you choose the size of the wedge to the Planck scale, you get it, and we believe that that's sufficient to tunnel, in a sense. That's sufficient to give a tunneling. You don't need to violate Einstein equations more than that. Look, we will compute this. It's just a matter of time. So
It's sort of like a pre-Big Bang, right?
Sorry?
Pre-Big Bang, there you don't pay exponential price.
Yeah. It's like him. I mean, you shouldn't complain about that because you're the last person who should. Yeah.
Yeah, if you have a region which allows you to violate energy conditions, you don't pay exponential price.
That's right.
Just go through, right?
That's right. That's right. Okay. Now.
I have a question. In region 3, you can imagine you had some effective equations of motion. And I think your boundary conditions would be data from the classical sampling. And it does so on the lower boundary.
Right.
And, but that's a slightly ill-posed problem, isn't it? We don't usually look for classical solutions to Cauchy surfaces, which are equal on the two Cauchy surfaces.
They're not equal. They have extrinsic curvature flipped. So it's going from this geometry to this geometry.
Not quite equal. You don't normally set data on two surfaces which are time-like separate. Maybe they're not time-like separate. Maybe the equations are different. But in any classical set of equations, that is what is it called? The sandwich problem.
Yeah.
And it's ill-posed.
Right. We know for sure, obviously, that there is no solution of the standard Einstein equation, right? Because that's so, right. I mean, if we allow ourselves arbitrary modification of the equation, we have a metric that interpolates. We can write a metric that interpolates the two. Of course, I mean, just stupidly. Yeah, stupidly, we can write a metric that interpolates. So then, of course, there is an equation that is satisfied. But that's what is that telling us? That's one of the. At the beginning, we were following that path. Let me go. I don't have much time. Let me go to the phenomenology. Suppose this is true. Okay, let's put this on a side for a moment. Whether this might be reasonable or not. Suppose this is true. Then we can see primordial black holes. There are primordial black holes. Are there primordial black holes in the universe? We don't know. The astrophysicists with whom I talk are taking the hypothesis very seriously. So there are some bounds that one can put observational, some ranges of masses. Other ranges of masses are open. But the story could be the following. Very simple. So early in the universe, there is a black hole that collapses, and look, remember, inside is a millisecond. So boom, boom. Outside is a billion, is 10 billion or 13 billion years. Then the black hole explodes, sends a signal, and we see it. That's the thing. How the hell do we get a observable wavelength from a Planck size? Well, if you take the Planck scale and you multiply, this is where the square root of m comes in. The ratio between the Hubble time and the Planck time is a large number that makes the phenomenon observable. So we expect two possible sort of signals from that. One is from the Hubble time, we can compute the mass. Okay, and I already gave you the answer. It's the mass of a small planet, which means a Schwarzschild radius of the order of a centimeter. Now, to the very brutal first approximation, if you have something exploding of the order of a centimeter, something in the signal will have a wavelength of a centimeter, right? So do we see centimeters, wavelength signals from the sky, burst, sudden, very strong, of this order? That's the first, that's what we call the low energy component. But then the matter coming in is supposed to come out. Now, if it was produced in the early universe when people expect primordial black hole to be produced, it's very hot at the time, it's high temperature. So there are many, say, photons of high temperature being trapped. Inside, nothing happens because it's just a short time inside. So what you expect to come out is high energy photons. So there's a high energy signal as well. Which energy? Well, the ones of the temperature when the primordial black holes were produced. So this is the expectation for the signal. And now is an interesting story. So there are some signals like that in the sky. The most interesting one is the low energy one, the fast radio burst, because there are no explanation. There are a number of, I'll come back to them, a number of very strong signals of a millimeter size, so not really centimeters, a little bit smaller, but not much, which have been seen by Arecibo, by Parker's observatory, and nobody knows what they are. How would we know? This is very pretty. Let's look at the low frequency one. Suppose we see one of the signals coming from far away, cosmological distances. Then the photons take time to come to us, so the lifetime has been shorter. If the lifetime has been shorter, the mass is smaller. If the mass is smaller, the Schwarzschild radius is smaller, and the wavelength emitted is smaller. And this is going to compensate the redshift due to the fact that this is far away. So instead of the standard redshift curve, you would see a relation between distance and wavelength flattened. So if we see many of these fast radio bursts, and fast radio bursts is easy to see the distance because in the radio, people can estimate, astronomers can estimate the distance from the dispersion because the galactic medium is not fully transparent to there's dispersion in the microwave. So we know the distance, we measure the observed wavelength. If instead of being the standard Hubble, the standard one of cosmological shift, it comes out flattened, then we don't know anything else that would have that. The nice part is that even the high energy signal would have a similar flattening. Why? Because, again, if they are emitted far away, then they live less. If they lived less, they're smaller. If they're smaller, according to standard theory of black hole, primordial black hole formation, they were produced a little bit earlier because the size of the black hole is determined by the horizon, the size of the horizon in the early universe. So first they produce a small one, then the other one. But if they were produced earlier, it's hotter. So there's higher temperature. So the emitted photon are higher temperature, shorter wavelength, once again. So again, you have an effect compensating. So there will be a smoking gun, in a sense, for seeing, yes, these signals come from this effect. I don't matter here. I mean, people doing phenomenology says that there's nothing else that would have this flattened curve. Even if we don't see the single events, the integrated emission of these, instead of being a standard Planckian curve, would be a deformed Planckian curve. Oops, sorry. A deformed Planckian curve. So people in phenomenology expect that this would be possibly, could be detected even from their accumulated effect of many of them. So here are the short-range gamma ray bursts. They are of course observed by radio telescope. Again, we are talking about millimeter and centimeters. This is one of the actual signals that has been observed. There are many observed. Maybe 20 have been observed so far. But there's a lot of excitement about because nobody knows what they are. There are other, and they pretty much match all the characteristic that an exploding black hole could have. It's shorter. There's nothing else associated to it. There's no repetition. In fact, one of them was repeated, but it seems that it's a lensing. We see it twice because it was lensed. It's a very large flux. Of course, we cannot estimate the flux because we don't know how much an exploding black hole, how much of its energy is transformed in one form or the other.
How long did it first last?
Milliseconds. Okay. So let me just, sorry, this is, I want to go faster here. I stole this transparency from one of the people doing phenomenology. I just want to go ahead. Please go ahead. Okay, so that's the summary. So technical result number one, it's a result in classical generativity. There is a solution of Einstein equations, which has a black hole in the past, a white hole in the future, and is well defined as a solution of Einstein equation, except in a compact region. Okay. Therefore, I would say one can expect tunneling, because the Einstein equation can be violated by quantum effect in this region. Gabriele was saying, well, and others, you were saying, well, at first one might say, okay, but this is suppressed by exponentially suppressed, so there's no astrophysical relevance, whatever, it's much longer than the Hawking radiation. We have a number of arguments indicating that the lifetime could be of the order of m squared, and loop quantum gravity allows you a calculation to first order in approximation, which we are doing, and it gives a finite expression, which for the moment is just a complicated sum of integrals. We are manipulating them, I hope, soon, if you stay tuned, to give you a clear answer what that expression gives. We think we see already that it might confirm the m square argument. If there is an m square lifetime, then of course it has huge implications for information, firewalls, which I don't want to discuss because it opens a can of worms. But certainly it would shorten enormously the life of the whole. What comes in comes out, simply. But more interesting, in my opinion, it might lead to observations, and in fact there are a number of observations that might already be these things, and there is a wavelength to distance relation predicted from this phenomenon that could tell us in a few years, if this are observed, whether the signals we see might be of this origin of else. Thank you.